In this session, we'll talk a little bit about variables, specifically the different types of variables that you may encounter when solving real life problems. So let's start with the basic definition of a variable. A variable is any feature or characteristic that varies across individuals in a group. So this group could be a large group of individuals that we're interested in called a population, or it could be a subset of the population which we call a sample. We typically use a sample when the entire group of individuals in the population is not visible to us or not visible to us. So the idea is to perform some sort of a statistical procedure using sample data and then generalize that information back to the population. So variable could come from the population or the sample, but regardless of that, a variable is defined as any feature or characteristic that varies across individuals in a group. We'll assume for simplicity that our data is from sample data. So a variable is a characteristic that varies across individuals in our sample. The opposite of a variable is a constant. A constant is a characteristic that does not vary across individuals in a group. So if you ask everybody the same question in a group of people and everybody responds the same way, they give you the same answer, then that question does not represent a variable, it's a constant. So for example, if you ask a group of individuals whether or not they smoke, so you ask a simple question to 20 individuals in a group, in a classroom for example, are you a smoker? And each individual person responds the same way to this question. Each person says no. Since we have all non-smokers in this classroom, smoking status, this attribute or characteristic, is not a variable, it's a constant. Today we'll talk a little bit about the different types of variables that exist and how do we identify these different types of variables. So a variable is any characteristic or feature that varies across individuals. An easy way to think about a variable is to think about a simple table, a flat data table that has many rows and columns. Right? The number of rows and columns depends on how many people you have in the sample. I'm going to construct a very simple table here that has multiple rows and columns. My example has 3 rows and 5 columns. Each row in this format is called an observation, and each column is called a variable. A variable has different names: dimension, vector, field, attribute, characteristic, feature. These are all different names for a variable. A row also has different names. A row or observation is the same thing: case, respondent, participant, instance, example. These are all the different terms that are used for the same concept. So in my example, we have a sample size of 5, which means there are 5 observations: number 1, number 2, number 3 in the 3rd row, number 4 is our 4th row, and 5th row. And we have 3 variables: variable 1, variable 2, and variable 3. Remember that in order for a column to be qualified as a variable, the values in that variable should not all be the same. So as long as any 2 values in a column are different from each other, that column represents a variable. So in this example, let's say our unit of analysis is actually a person. So my observation number 1 is actually person number 1. Observation number 2 is person number 2, person number 3, person number 4. My handwriting is not so good. And person number 5 is in the 5th row. So we have a group of persons in this data set, in this table. And these persons, these group of individuals, have different features that are represented in columns. These variables represent the different features that people have. So let's say this is a group of students. The 5 person in our sample are actually students, and these variables are age of all these students, and we have information on let's say the smoking status of these individuals, and we have also information on their social status. And I'm going to measure social status in terms of a grouping variable. I'll explain what a grouping variable is, but right now just assume that we do not have numeric values. We are just placing individuals into different groups. We have some persons in our sample that belong to low socioeconomic status, for example. They come from backgrounds that are maybe not so rich, they do not have a lot of money. And then we have some from medium socioeconomic status. So these are individuals who are kind of from the middle class, another person from low socioeconomic status, and then one person whose household whose family is rich or is well off. And then we also have age values of these students. So I'm just making up some numbers here. We have different ages for these 5 persons. And also their smoking status. I'll use S for smoker and S for non-smoker. So we'll assume that the first 3 individuals are all non-smokers. The 4th person is a smoker, and the last person is also a non-smoker. Notice that in all of these columns we have multiple values. As long as there are at least 2 values in a column, that column represents a variable. In order to qualify as a constant, all the values in a column should be exactly the same. There should be no variation whatsoever. As long as we see variation in a column, we are dealing with a variable. So we understand what a variable is. There are 2 basic types of variables. A variable is either qualitative or it is quantitative. Right? So any variable that you come across, once you have decided how you're going to use that variable in a statistical model, you're going to treat it either this variable either as a qualitative variable or a quantitative variable. These are the only 2 types of variables that you're going to encounter. Now, when you're looking at statistics textbooks, or more particularly, when you're looking at data mining textbooks, which is a kind of a specialized area of statistics, where a lot of computer science is involved. In these textbooks, you'll see reference to, when they talk about types of data, the authors, they make reference to additional types of data, like sound data or data that's in the form of images or pictures or videos and so on and so forth, which is fine from their point of view. I'm talking about the point of view where you're using a particular variable in a statistical method. Like, for example, when we get to Education 520, we'll talk about methods like regression analysis and analysis of variance and so on and so forth. In order to use a variable in those methods, you have to make a decision. You either treat that variable as a qualitative variable or a quantitative variable. These are the only 2 ways you can add a variable in a statistical model. So a variable is either a qualitative variable or it's a quantitative variable. Qualitative variables are also known as categorical variables. It's just a synonymous term for qualitative. And quantitative variables have another name. Quantitative variables are also known as numeric variables. Right, so these are the 2 types of variables that you will encounter when you're solving real-world problems after collecting data, running statistical models, and so on. Now, there are 2 important terms that are applicable here. The 2 types that I have just described, well, I have just listed them, not described them. I'll describe them in a minute. But qualitative and quantitative, the 2 types of variables that I've just listed in this tree diagram, they have 2 important characteristics. These 2 types of variables are mutually exclusive, and these 2 types of variables are also collectively exhaustive. These are very important terms, and they are widely used in probability theory, and they have very specific meaning. Mutually exclusive means that if we have 2 choices, A and B, then either A can occur or B can occur, but both can't be true at the same time. Both cannot occur at the same time. Right? So either, in terms of our 2 variable types, a variable that you come across is either qualitative or quantitative. It can be both at the same time. Collectively exhaustive is also a very specific term. Collectively exhaustive means that we have accounted for all possibilities, or in this case, all types of variables that are possible. We haven't left anything out of the list. So any variable that we come across, it has to be one of these. It is either qualitative or quantitative. There is no third possibility out there. Right? So taken together, these 2 properties mean, these 2 terms indicate that any variable that you're dealing with is either qualitative or it's quantitative. It has to be one of these 2 because there is no third type. And at the same time, it can be both. It will be either qualitative or quantitative, but can be both at the same time. All right, so that's mutually exclusive, either this or that, and collectively exhaustive. We're accounting for everything here. There is no third type of variable that's left out of the list. Now, if this concept is a little bit difficult to understand, then try to imagine a coin toss. Coin toss example works very well for me too. So a coin toss has two possible outcomes, or there are two possibilities associated with a coin toss. One possibility is called heads, and the other possibility is called tails. Or depending on when you toss the coin, one face or the other will show up. One of these is called the heads, the other is called the tails. So coin toss has outcomes that are mutually exclusive and collectively exhaustive. When you toss a coin, you know for a fact, in fact, even before you have tossed a coin, you know for a fact that it will be heads or tails. It's one of these two possibilities. You're not leaving out anything else. You know for a fact that there is a third possibility that can occur. You're accounting for all different outcomes that are possible when you toss a coin. So those two possibilities are heads or tails, and these are collectively exhaustive outcomes. There is no third possibility, so you know for a fact when you toss a coin, you will see one of these two things. You will either see heads or you will see tails. And at the same time, these are mutually exclusive possibilities. These are mutually exclusive because you will either observe heads or you will observe tails, but you cannot observe both at the same time. So at the end of the day, coin toss outcomes, heads and tails, these are two possibilities that are mutually exclusive and collectively exhaustive. These are mutually exclusive because both cannot occur at the same time, and they're collectively exhaustive because it's a guarantee that one of these will occur when you toss a coin. Similarly, a variable has two types, qualitative and quantitative, that are mutually exclusive and collectively exhaustive. It means that any variable that you come across, it's either qualitative or it's quantitative. It has to be one of these, but it can't be both at the same time. Now, these two types of variables have subtypes. Let me just complete the tree here, the tree diagram here. I will list those types, two subtypes of each of these two primary types of variables, and then I'll explain all of these different types. What's the difference between categorical and numeric, and what's the difference between the subtypes? So categorical variables have two subtypes. These are called nominal and ordinal. And quantitative variables also have two subtypes. These are called interval and ratio. Right. So first of all, what's the difference between categorical and numeric variables? All right. So let's start with the categorical variables. A categorical variable allows you to divide your group of interest, whether it's the sample or population. For now, let's assume that we're working with a sample. That's what I also assumed in my previous example. So a categorical variable is a variable that allows you to split your sample into subgroups. So for example, if I have 40 different students in my classroom and I split them into two groups based on their smoking status, one group of smokers, the other group is comprised of non-smokers, then smoking status in this case is an example of a categorical variable. I've been able to create categories or groups of observations in my sample. Another example of a categorical variable is the gender of a person. Some individuals are male, some are female. I'm creating two subgroups in my sample. I'm dividing my sample into two groups, all males in one group, all females in the other group. Another example is socioeconomic status. For example, low, medium, and high. Socioeconomic status of low means somebody is poor, high means that person is rich, and medium means that person belongs to the middle class, has some sort of a medium income. So socioeconomic status or social status is an example of a categorical variable. If I have 100 customers, for example, in my sample, if I'm working with, say, business data, I have 100 customers, then I can divide those customers into three different groups based on their income. One group could be low socioeconomic group, they have low income, another is medium group, another is a high socioeconomic status group. This is also a categorical variable that allows me to divide my sample into subgroups. Other examples are people who live in United States versus individuals who live outside the United States, individuals who live in Kenya versus individuals who live outside Kenya, a person who was born in Asia versus all persons who were not born in Asia. Your continent of birth is an example, or country of birth is also an example of a categorical variable. You're splitting individuals based on where they were born. All individuals who were based in Tanzania are in this group. All individuals who were born in India, they go to the second group. All individuals who were born in Libya, they are in the third group. All individuals from United Kingdom, they are in the fourth group, and so on. So we are dividing people into different groups based on the country, their country of birth. All of these are examples of categorical variables. Now, once you have examined a variable and you have established that this variable is not categorical, then there is only one possibility left. That variable has to be numeric, because there is no other choice here. If a variable is not categorical, then it has to be numeric. There are only two branches in this tree. However, let's treat a numerical variable specifically. Let's have a specific definition. A numeric variable is a variable that provides a specific numeric response for each and every observation in the sample. So in other words, we're talking about a column that consists of numbers. In my example over here, age is an example of a numeric variable because I have all numbers in this column. But this is not the only condition that is required for a variable to be numeric. Not only should I have numbers in a column, not only should I have a numeric response from each and every individual in my sample. In addition to that, I should be able to perform basic arithmetic operations like addition and subtraction on these numbers. This is the bare minimum. If I cannot perform addition or subtraction on the values, numeric values in a column, then my variable is not a numeric variable. Here is an example of this. So here I am in the fourth column in my data set. I am going to collect some information about the telephone numbers of these 5 individuals. So we have some individuals in this sample. We have 5 people in this sample, and I'm going to ask for their phone numbers. That's another variable of interest. It's a variable because these individuals, unless maybe they're related to each other, which is very unlikely, if in a classroom, if these are 5 students, chances are that these students have different phone numbers. Unless they're related, when if they're sharing the same phone number, then of course it's possible for the phone number to be a constant. But we'll assume that the contact phone numbers of these 5 individuals are not the same. So here I'm going to use the example of area codes that are common in the US, that are used in the US phone numbering system. In other countries, there are similar systems. The codes might be different, the format and the length of the phone number might be different, but this example is still applicable. So let's say in the US, the phone numbers are 10 digits. So let's say person number 1 has this phone number, 703-112-3597. I'm just making up some numbers, some hypothetical number here. So person number 1 has a phone number that starts with 703, right? That's the 10-digit phone number for this person. Person number 2 lives in a different area code, right? So this person's phone number starts with 571, right? So 571 is the area code for this person, and then 1112233, some number like that, and so on and so forth, right? So we have a telephone number for each of the 5 individuals in this sample. Now I do have numbers in this column, so the information seems as if it's numeric information, but that is not really the case, because the second test, that we're able to perform arithmetic operations like addition and subtraction on these numbers, that is not passed. That criterion is not passed by this column. So I do see that there are numbers in this column. That's the first condition, but I cannot combine these numbers or compare them with each other in any meaningful way. So I cannot, for example, say that I'm person number 1, my phone number starts with 703. That's a better phone number or a bigger phone number than 571, because 571 is a smaller number. So my phone number is higher or bigger or better than 571. That is a ridiculous, nonsensical statement. 703 and 571 here are just area codes. They just mean that the person's phone number belongs to a different region or location, a different geographical area. Other than that, these numbers have no significance. So phone number is an example of a categorical variable. It's not a numeric variable, even though the information in this column looks like numbers. These are not actually numbers that can be compared meaningfully with each other. So it's not numeric information. Age, on the other hand, was an example of a numeric variable, because not only um, can I see numeric values in this column, but I can also pick any two numbers in this column. I can compare them meaningfully with each other. So for example, I can say that the person who's 19 years old is exactly 1 year more than the person who's 18 years old. So I've just taken the difference between 19 and 18 and interpreted the difference without any problem. The person who's 19 is 1 year older than the person who's 18. Or I can add two numbers together. For example, I can take the average age of the first two individuals in the sample. The average age is 18 plus 19 divided by 2, which is equal to 18.5. In fact, this is a very specific kind of average. In statistics, this is called the arithmetic mean. In a separate session, we'll actually talk about these different types of averages. So for now, just think of this as a simple average, the kind of average that we all learn about in high school. So the average age of the first two individuals in our sample is the sum of 18 plus 19 divided by 2. I have been able to take the sum of these two ages. That's a meaningful operation here, right? It makes sense. I could not take the sum of these phone numbers, take the average phone number, for example. That would not make any sense. So age is different from phone number. I not only see numeric values in this column, but age values can also be compared with each other in terms of magnitude. Specifically, I can perform operations like subtraction or addition on this variable. These were not possible with the phone number column. So phone number was not a numeric variable. Age is a numeric variable. Phone number is a categorical variable. In fact, it's a very specific kind of categorical variable. I call it special because if each individual person in our sample has a different phone number in the phone number column, then it's a categorical variable with 5 different groups, and there is only one person in each group. So a very special kind of categorical variable where the number of groups is actually equal to the number of people in the sample, number of persons in the sample. All right, so back to our two primary types of variables. A categorical variable allows you to divide your sample into subgroups. We can see an example of this in smoking status. Smoking status is a categorical variable. Some individuals in our sample are smokers, others are non-smokers. So for example, I see there is one group of individuals, there is only one person in this group, and that person is a smoker. And there are 4 individuals in the other group, and these individuals are non-smokers. So what I have done here is I have effectively taken the 5 individuals in my sample and divided them into 2 subgroups. There are 4 individuals in one group, non-smokers, and there is one individual in the second group, that's the group of smokers. So there are 2 groups of individuals here. I'm creating groups or categories out of my original sample. I'm splitting my sample into subgroups. Whenever you do that, you're dealing with a categorical variable. Whichever characteristic allows you to split your sample into subgroups is a categorical variable. And then we saw an example of numeric variables where we have numbers in a column, and these numbers can be meaningfully compared with each other in terms of their magnitude. We can perform arithmetic operations like addition or subtraction. They make sense for numeric variables. So 2 basic types of variables that are mutually exclusive and collectively exhaustive. Any variable that you come across is either qualitative or quantitative. It's either categorical or numeric. It has to be one of these, and it can't be both of these at the same time. Now let's talk a little bit about the subtypes of these variables. Categorical variables have 2 subtypes that are nominal and ordinal. Both of these create subgroups in a sample. So what's the difference between nominal and ordinal? The difference is that when you list the subgroups or the different values of your categorical variable, if there is a meaningful order to those categories, then your variable is ordinal. Otherwise, your variable is nominal. So if order exists, your variable is ordinal. Easy way to remember that. And if there is no order, then your variable is nominal. Let's take a look at a couple of examples. Let's say we ask individuals in our sample for their favorite color. So I'm going to expand my sample size a little bit. Let's assume that I have 40 students in my classroom, and I ask each individual person, which of the following four colors do you prefer? Red, green, blue, and yellow. So we're not asking each person for their favorite color, because then, people will have dozens of colors, pink and silver and gold and blue and red and whatnot. So we are not really asking about people's favorite color, because the list will be too long. The question we are asking is, which of these four colors do you like the most? And each person will assume cooperates and gives us an answer. So at the end of the day, some individuals like the color red, some individuals like the color green, some individuals like blue, and some individuals like yellow. Oops, I think that's more than 40 individuals. I have to adjust these total a little bit. Let's change the first total to 10. All right, so I have 10 individuals here, plus 15, that's 25, plus another 15. So that's a total of 40 individuals in this column. So we surveyed 40 individuals. We asked them, which of the four colors, red, green, blue, yellow, do you like the most? And some individuals said they like red, some individuals said they like green, other individuals like blue or yellow, for a total of 40 individuals. So we have complete information. Everybody gave us an answer. Notice that what I have done here is I have effectively taken my sample size of 40 and I have split it into four groups. Individuals who like red, individuals who like green, individuals who like blue, and individuals who like yellow. So I've taken a sample and split it into subgroups. My variable X is color. Color is the variable that allows me to split my sample into subgroups, so color is a categorical variable. However, it's a special kind of a categorical variable. It's a nominal variable, and the reason it's nominal is because there's no way I can arrange these four colors in a meaningful ascending or descending order. So for example, I can say that red is more of a color than green, or green is more of a color than red, or make some other comparisons like that. Remember, the alphabetical order does not count. If you take these four colors and actually translate them into a different language, the alphabetical order will be very different. Right now, the alphabetical order is blue, because B comes very early in the alphabet, followed by green, and then red, and finally yellow, because yellow starts with Y and Y is very close to the end of the alphabet. This is the alphabetical order. In statistics, this alphabetical order is useless, it's meaningless. It does not have any mathematical information in it. So we don't care about this mathematical order. What we care about is, we don't care about this alphabetical order. What we care about is some sort of an ascending or descending order of magnitude, where you can pick any two values in the list and compare those values with each other in terms of their magnitude. Right now, for variable X, which is color, I'm just using notation X to denote that variable. In statistics, like mathematics, we often use X, Y, and Z to represent variables. So my variable X, preferred color, is a nominal variable, because there's no way I can list these colors in a meaningful order. I cannot say that green is more of a color than red. These are just personal preferences. Some people like green, some people like red. It's like saying that some people like pizza, some people like fish, some people like rice. These are all different choices that people make. These are different preferences that people have. Just because these are different does not mean that one is better than the other. You cannot say, for example, rice is more of a food than pizza or other way around. Remember, we are not looking at the number of calories in these foods or the price of these foods. We are just comparing these names of different foods with each other, just like we are comparing the different names of colors with each other. We're not looking at the intensity of these colors on some sort of a spectrum or anything like that. We're just comparing four names with each other. And since alphabetical order is of no use to us in statistics, we really cannot arrange these four colors in a meaningful. For example, I can take these I can take these four colors and I can list them in a different order, right? So instead of red, green, blue, yellow, I could have listed these four colors as, I could have started with green, and then yellow, red, and blue could be at the end. This list is as good as my original list. Different way of doing the same thing, basically. right? So I cannot say that if I pick any two values in column X, one is greater than the other or it's smaller than the other. I cannot compare these values in terms of magnitude. So this is an example of a nominal variable. Now, if I did have a different values for a different variable and I could pick any two values of that variable and compare those values in terms of magnitude in a meaningful way, then that variable would be an ordinal variable. So let me use an example of an ordinal variable here. One very simple example I can think of is the highest level of education that a person has completed. So let's say we have a couple of individuals in our sample and we're asking them about their highest level of education. So these are adults, and let's say we have 100 adults in our sample, and these are the answer choices. I'll limit myself to just 6 answer choices. We classify a person as someone who has never completed high school, somebody who completed high school, has some college education, has completed a bachelor's degree, has completed a master's degree, or has completed a PhD. Right, so PhD is the highest level of education here. And let's have some sample sizes. So I'm going to denote education. I'm going to denote education with Y here, right? So that's the symbol for education. And in the next column, I'll just put the group sizes. So we are dividing these 100 individuals into 6 subgroups. Out of these 100 individuals, let's say we have 30 individuals with a bachelor's degree. 20 individuals have completed some college education. They never completed a bachelor's degree, but maybe spent 1 or 2 years in college. And then we have some individuals with high school education, some individuals who never completed high school. That's a total of 30, 40, 50, 65 individuals. Maybe another 20 individuals who have a master's degree, and the remaining individuals have a PhD. So 30, 40, 50, 60, 70, 85. Let's make this 15 and let's make this 5, because there are typically fewer individuals with higher levels of education. And I can make a little bit more of an adjustment. I would like to make it a distribution where the frequencies are sort of smaller at the extremes. All right, so this is 15 and this is 10. So I have 15 over here. Now let's do a count just to make sure that we have frequencies adding up to 100. Frequencies are the same thing as group sizes or counts, the number of times each value repeats itself in a column. So we have 25 plus 50, that's 75, plus another 25, that's a total of 100. So we have the education status of 100 individuals who are a part of our sample. Notice that education is a categorical variable because we have just split 100 individuals in our sample into 6 subgroups based on their highest level of education. So this is definitely a categorical variable, but the question is it a nominal variable or is it an ordinal variable? And the answer is that if I pick any two values in this column, in the Y column, if I pick any two values of education, can I meaningfully compare them with each other? If the answer to this question is yes, then this is an ordinal variable, otherwise it's a nominal variable. So let's pick any two values of education. So I'm going to pick bachelor's and PhD. Is it possible for me to say that a bachelor's level of education is less than a doctoral level of education? Clearly the answer is yes. So I can do this comparison meaningfully. I can say that bachelor's represents a lower level of education, the variable that I was trying to measure, as compared to PhD. Or I can say that master's is a higher level of education than a high school diploma. Since I can compare these two values of education meaningfully, education is an ordinal variable. There is a specific order to these categories. Everybody who is a PhD has a higher level of education than everybody who has a master's degree. A master's level of education is a higher level of education compared to a bachelor's degree, which is higher compared to some college, which is a higher level of education compared to high school diploma, and so on and so forth. So we see a natural ascending order in these categories as they go from top to bottom in this list. Or you can also say that there is a natural descending order as they go from bottom to top in this list. As they go from PhD to less than high school, the level of education is decreasing. And as they go from less than high school to PhD, the level of education is increasing. So this is an example of an ordinal variable. Any variable that allows us to compare two of its values in terms of magnitude, which means we can use greater than or less than signs. Any variable that allows us to do that is an ordinal variable. All right, so we just completed a discussion of the two subtypes of categorical variables, nominal and ordinal. Nominal variables, which divide a sample into subgroups, but we cannot really compare the values of that variable with each other. For example, some individuals live in Brazil, some individuals live in Canada, and some individuals live in Algeria. And so these are three different countries. X represents the name of a country. Is there any meaningful order in these names? Can I compare Brazil and Canada and say one is more of a name compared to another? Remember, we're not talking about the size of these countries or what is the average income in these countries or how many people live in those countries or the size of the military or any other metric, inflation rate, unemployment rate. We are just comparing these three names with each other. Is Canada a better name than Brazil? The answer is clearly no. It's just a name. Just like people have different names, right? So in this case, since I cannot arrange the values of my variable in a particular ascending or descending order, remember the alphabetical order does not make any useful contribution. So in statistics, so alphabetical order is something that we're totally ignoring. We don't care about the alphabetical order in statistics. Other than that, since I cannot compare the values of this variable in a meaningful ascending or descending order, this is an example of a nominal variable. I am dividing the 30 individuals in my sample into subgroups. 10 of them live in Canada, 15 of them live in Brazil, and 5 live in Algeria. So I have divided my sample of 30 individuals into 3 subgroups. This is clearly a categorical variable, but on top of that, it's a special kind of a categorical variable called a nominal variable because I cannot arrange these 3 values of x in a particular meaningful ascending or descending order. Whenever I can arrange the values in a meaningful ascending or descending order, I am dealing with an ordinal variable, the second type of categorical variable. Now, numeric variables, as we have learned, have numbers in a column, and we can perform operations like addition and subtraction on those numbers. So how do we know whether this numeric variable is an interval variable or a ratio variable? The test here is the presence or absence of something called the true zero. If the true zero is present for a variable, then that variable is a ratio variable. So we really need to get a handle on what is meant by true zero. If true zero is not present, then the numeric variable is an interval variable. Right? So true zero is present, the variable is ratio. True zero is not present, the corresponding variable is interval. So what is this true zero? We really need to understand this. True zero is the value 0, and it does not have to be actually a value that's possible in your sample. It could be a completely hypothetical value. If the value 0 means the absence of the attribute or characteristic that you're measuring, then your underlying variable has the true zero and it's a ratio variable, which means you can interpret the ratios of values on that variable. All right, let me say that again. If the value 0 has this special meaning that it represents the absence of an attribute that you're measuring, then this variable has true 0. This column, this variable has this attribute called true 0, and we can interpret the ratios of values on that variable. If the true 0 is not present, then the variable is an interval. Ratio and intervals, these are two mutually exclusive and collectively exhaustive categories. So a variable that is not ratio, by definition, is a variable that is interval. These are subtypes of numeric variables. Just like qualitative and quantitative variables are mutually exclusive and collectively exhaustive, these two properties also apply to all four subtypes of variables that we have seen so far. Any variable that you come across is either nominal or ordinal or interval or ratio. It can't be more than one at the same time, and it has to be one of these because there is no fifth type of variable in this list. Any variable that you come across eventually will be one of these four types of variables. So we were talking about the ratio variable, and we said that a ratio variable has something called the true zero. Let's take a look at some examples of true zero. So here I have an example where we are looking at the age of individuals in our sample. So we have person number 1, person number 2, person number 3, and 4 individuals in this column. And these are the ages of those individuals. Person number 1 is 20 years old, another is 19, 18, last person in our column is 21 years old. This is clearly a numeric variable. There is no doubt about that because I can add numbers together in this column, and that has an interpretation, and I can take the difference between two numbers, any two numbers in this column, and that has an interpretation. So this is a numeric variable. I can perform addition and subtraction operations on the values of this variable. But is this variable interval or ratio? How do we determine that? Well, we have to think about the value 0 as it applies to this column. Now clearly we will never have an actual person in our sample who's 0 years old. Somebody who's 0 years old does not exist, right? So 0 here is a hypothetical value. But let's assume that a value of 0 were possible for this variable. What does this value of 0 represent? A value of 0 for age means the absence of age, the attribute that we are trying to measure. Whenever 0 has this special meaning, whenever the value 0 in a column represents the the absence of the variable that we're trying to measure, that 0 value is called the true 0. Let me say that in another time. Whenever the value 0 represents the absence of the attribute that we're trying to measure, then that attribute has the true 0. It's called a ratio variable. And we can interpret the ratios of values on that variable. So for example, for age, I can say that a person who's 40 years old is twice as old as a person who is 20 years old. I just performed a division operation here. 40 divided by 20 is 2. So a person who's 40 years old is twice as old as the person who's 20 years old. I can do this, I can interpret this ratio because my underlying variable age is a ratio. And age is a ratio variable because it has this true 0. The value 0 for age means the absence of age. Age does not exist. Somebody who's 0 years old does not have an age. Obviously, we will never meet a person who's 0 years old because that person does not exist. But hypothetically, if somebody had an age of 0, it means the absence of age. Another example. Let's say you're interested in buying gasoline. Gasoline is the same thing as petrol or petroleum. So you want to buy petrol. So you go to a gas station or a petrol station, and the gas is selling for different prices. I'm going to use gallons, which is the unit typically used in the United States. In other countries, other units are used like liters, for example. So I'm going to measure the price of gasoline, which is petrol, in dollars per gallon. All right, so we have price of gasoline. Let me erase this. We have price measured in dollars per gallon. All right, so this is the price of gasoline. And we go to 4 different gas stations or petrol stations. Number 1, number 2. So our unit of analysis in this example is a petrol station. So you go to 4 different stations and we observe the price. At station number 1, gasoline is being sold for $2 per gallon. Station number 2 is selling the same gasoline, no difference, same product, no difference in quality, at $3.50 per gallon. And then we have a gasoline station which is selling gas at $4 per gallon. And finally, we have a station that is selling gas at $2.25 per gallon. I'm obviously making up these numbers. This is all hypothetical data. So first of all, is this a numeric variable? Yes or no? The answer is yes. I see numbers in this column, and I can also interpret the numbers in terms of their differences and their sums. So for example, I can compare the first two values in this column and say that gas station number 2 is selling gasoline at a rate of $1.50 higher than gas station 1. So gas at gas station 2 is $1.50 per gallon more expensive than gas station 1. I just took the difference between these two numbers, $3.50 per gallon minus $2, and I was able to interpret this difference, $1.50, without any problem. So price is definitely a numeric variable. There's no doubt about that. However, we have learned that there are two types of numeric variables. So how do we know whether price is numeric or is interval or ratio? Price is a numeric variable, but is it interval or is it a ratio variable? Well, the test again is the presence or absence of this true zero. So let's imagine a price of 0 in this column. Now clearly again this is a hypothetical value because nobody will sell petrol at $0 per gallon, because then they are giving it out for free. They're really not going to earn any money on this sale. So we are unlikely to actually observe a price of $0 for gasoline. But let's say this price actually existed. What does this mean? 0 in this column would mean the absence of price. $0 per gallon, this special value 0, has a very specific meaning here. The value 0 means the absence of price, the variable that we are trying to measure in this column. Just like the value 0 for age meant the absence of age in the age column. So for this reason, since the true 0 exists, I can compare any two values of the price variable with each other. So for example, I can take the number 2 and take the number 4. These are the two values that I see in the price column, and I can say that a price of $4 is twice as high as a price of $2. I just divided $4 by $2. The answer is 2, and I was able to interpret this number without any problem whatsoever. The price is another example of a ratio variable. Let's use another example here. This time I'll use a variable where the value 0 actually makes sense for our sample. So this time our unit of analysis is a day, and we are looking at the number of units of a product that are produced in a particular company. So let's say this is a company that makes computers, and on day number 1 this company produced 500 computers. Q here is for quantity of computers produced. This is the total production that takes place on a particular day. On day number 2, the number of computers produced was 387. On day number 3, only 100 computers were produced. On day number 4, all the workers went on a strike and no computers were produced. The factory was closed. So 0 in this column actually makes sense. There will be 0 computers produced on a particular day when the company or the factory is closed, or when the workers are on strike, they don't come to the factory, or they come to the factory but do not work. So no production takes place. So I'm going to ask, what does this value 0 mean here? Does it have this special meaning that it represents the absence of the attribute that we're trying to measure? Does the value 0 in this column mean the absence of quantity, absence of any production? The answer is yes. 0 has this special meaning. 0 computers means no computers were produced, absence of any quantity produced on this particular day. So since 0 has this special meaning, the value 0 in this column represents the absence of the variable that we're trying to measure. And this 0 is a true 0. We say that Q has a true 0, and it's a ratio variable. So I can interpret the ratio of different values of this variable. For example, I can say that the day we produced 500 computers, production was 5 times as high as the day we produced 100 computers. I have no problem interpreting the ratio of these two numbers. 500 divided by 100 is 5, and I can perfectly interpret this number without any problem. So these are 3 examples of ratio variables: age, price of a product, quantity produced. Typically these ratio variables cannot take negative numbers, so you can never find somebody who is negative, who has a negative age, for example, or a price of gasoline being a negative number, or that you're producing negative 100 computers or negative 255 computers. These negative numbers do not make any sense whatsoever. So typically for ratio variables, you don't see negative numbers. Zero has a very special meaning. It means the absence of the attribute that you're trying to measure. And for this reason, we can interpret the ratios of values on this variable. So for example, I can say a person who's 40 years old is 4 times as old as the person who's 10 years old. I can interpret the ratio because a true zero exists and it's a ratio variable. Other examples of ratio variables are weight of a person measured in pounds, height of a person measured in inches, and so on and so forth. So how do we know when a variable is interval? Well, it's pretty simple. If a variable is not ratio, if a variable does not have true zero, then that variable has to be interval, because that's the only other type of numeric variables. These two are mutually exclusive and collectively exhaustive. Excuse me. And these two are mutually exclusive and collectively exhaustive categories. So variable that is not ratio, but we know it's numeric, well, that variable has to be interval. Similarly, for categorical variables, if we know that a variable is not nominal, then it has to be ordinal. There's no third type of variable here. All 4 types of variables that we have discussed so far, these are called, taken together, these are called scales of measurement. Scales of measurement or levels of measurement or types of variable or types of variables. These all mean the same thing. These are the 4 basic types of variables, and these are all mutually exclusive and collectively exhaustive. Any variable that you come across will eventually fit one of these 4 roles, and exactly one of these 4 roles. A variable can't be more than one of these 4 types. It will be exactly one of these types. Can be more than one of these types, and it has to be one of these types because I don't see any 5th item in the list here, right? So these are the only 4 types of variables. Before we close this discussion, let me talk a little bit about interval variables. So we have already established that for an interval variable, there is no true zero. So a variable that's not ratio is basically an interval variable. But let's take a look at a concrete example. I'm going to look at the example of temperature. Right? So this is temperature on a particular day, and this is measured in, let's say, degrees Fahrenheit. All right, so I'm going to measure temperature on different days during the year. On day 1, for example, let's say this is a hot day. It's in June. The temperature is about 90 degrees Fahrenheit. So we round the numbers to the nearest degree. On a different day during the year, this could be a different month, different season. Let's say this was winter. The temperature was 30 degrees Fahrenheit. On day 3, temperature was 45. Day 4, a different month, different day during the year, the temperature was 37. Day 5, temperature was -5, very cold, -5 degrees Fahrenheit. So we have numeric values in this column, and clearly this is a numeric variable because I can compare these numbers in terms of magnitude. I can add values in this column, subtract one value from the other, and interpret that without any problem. Comparing the first 2 values, the difference between these 2 days in temperature is 60 degrees. Right? That's the difference between 90 and 30. I can interpret the difference without any problem. So this is definitely a numeric variable. But how do we know whether this is an interval variable or a ratio variable? So let's think about the value 0 for this column. How would I interpret the value 0 if it existed in this column? 0 is actually a value that can exist, right? 0 degrees Fahrenheit is a possible temperature. It's bitterly cold, extremely cold, but it's a possible weather. What does this 0 degree Fahrenheit mean? Does it have a special meaning? Does 0 degree Fahrenheit mean the absence of temperature? Clearly, the answer to this question is no. Why? Because absence of temperature would be a situation where molecules and all atoms come to a standstill and nothing essentially moves. I shouldn't say atoms, actually. The molecules come to a standstill and nothing moves. So 0 degrees Fahrenheit, we know, is not that situation. 0 degrees Fahrenheit is very cold, but we can still move around with adequate clothing, with adequate protection. So 0 degrees Fahrenheit is not an absolute 0. This value 0 does not mean the absence of the attribute that we're trying to measure. In our previous examples, for instance, for age, 0 meant the absence of age. For price, 0 meant the absence of price. There was no price when we bought gasoline for $0, right? It's a hypothetical price, but zero means the absence of price. You don't need to pay anything. Value of zero for quantity means the absence of quantity or absence of any quantity of computers produced, any production. Zero does not have this meaning, this special meaning for temperature. Zero does not mean the absence of temperature. So this value zero for temperature is not a true zero, and our underlying scale is an interval scale. It's not a ratio scale. So for this reason, I should not interpret the ratios of values on this scale. I cannot say, for example, that the day it was 90 degrees Fahrenheit, it was 3 times as hot as the day it was 30 degrees Fahrenheit. That's a nonsensical statement. We cannot interpret ratios like this. We have an interval variable. If we had a true zero, then our underlying variable would be ratio, and we would be able to interpret ratios. Similarly, if I were measuring temperature in degrees Celsius, I cannot say that the day it was 50 degrees centigrade, it was twice as hot as the day it was 25 degrees centigrade. This ratio cannot be interpreted because this is an interval variable. This is an incorrect conclusion, incorrect statement. Right? So that's what an interval variable is. So just to summarize, a variable is any attribute that varies across individuals in a group, in a sample or a population. And this is different from a constant. A constant is basically the same value repeated in a column without any variation. So we have some examples of variables in this column: age, smoking status, socioeconomic status, phone number. For people in our sample, these were all examples of variables. There are two basic types of variables. Any variable that allows you to split your sample into subgroups is called categorical. And any variable that gives you specific numeric values from each respondent, and these numbers can be compared meaningfully with each other, and you can perform operations like addition or subtraction, that variable is called numeric. Each of these two types of variables, categorical and numeric, have subtypes, two subtypes. Categorical subtypes are nominal and ordinal, and numeric subtypes are interval and ratio. Nominal and ordinal variables both split a sample into subgroups. The difference is that for nominal variables, you cannot compare two values of that variable in terms of magnitude with each other. You cannot say that one is greater than the other, one is larger than the other. For an ordinal variable, you can compare two values of that variable with each other. You can say that one is larger than the other or smaller than the other. So ordinal variables have values that can be compared in terms of magnitude. So we can perform operations like greater than or less than on these variables. For nominal variables, we cannot do this. For nominal variables, the only operation that makes sense is when you compare two values with each other and say whether the values are equal or not. So for example, in terms of our raw data, in the color example, our raw data would look like this. X represents color, and we have these different observations, number 1, number 2, number 3, and so on and so forth. We have 40 observations in this sample because we have 40 people. Excuse me. We have 40 people in this sample, so there are 40 rows in this table. 40 observations or 40 rows. So from each of these observations, we are getting a color. Person number 1 liked the color blue. Person number 2 liked the color yellow. Person number 3 said they like the color green, and so on and so forth. So if I pick any two values in this column, I cannot arrange those values in a meaningful order. I cannot say that one is bigger than the other color, or is better than the other color, or it has more color than the other, or anything like that. That does not make any sense for a nominal variable. The values of a nominal variable cannot be arranged in a particular ascending or descending order. The only thing I can do is I can compare two values with each other, like for example the x value for the first two observations, and say whether those values are equal to each other or not equal to each other. In this example, the first person likes the color blue, second person likes the color yellow, so these two values are not equal to each other. Let's have a person number 4 here who also likes blue. If I compare person 1 with person 4, their x values are the same. So the only two operations I can perform for nominal variables are whether two values of that variable are equal to each other or not equal to each other. For ordinal variables, in addition to everything that we could do with nominal variables, we can also perform comparisons. We can compare values of an ordinal variable with each other in terms of magnitude. With an interval variable, all of these previous operations are available to us, but now we can also do addition and subtraction. So for instance, in our temperature example, where temperature was a nominal variable, I can take the difference between any two numbers in this column and interpret that difference without any problem. So for example, I can say that on day 3, temperature was 45 degrees and on day 2, temperature was 30 degrees. The difference between these two is 15 degrees. In other words, on day 3, temperature was 15 degrees more than that on day 2. That is perfectly normal interpretation. I can interpret numbers like this. Similarly, I can take an average, which means first taking the sum of two numbers for an interval variable. That's also allowed. What I cannot do is for interval variables, I cannot interpret ratios of values. I cannot say 90 degrees is 3 times as high as 30 degrees Fahrenheit or twice as high as 45 degrees Fahrenheit, because that would be a misinterpretation. For ratio variables, we can do everything that we could do with interval variables, but now we can also perform operations like division and multiplication. Remember, multiplication is just another form of division. When you say you're dividing 3 by 2, this is the same thing as saying 3 times 1 over 2. So it's very easy for me to convert a division operation into a multiplication operation. These are basically two different ways of looking at the same thing. So now I have all of these various operations available to me. So you can clearly see that as we go from left to right, our scale of measurement is becoming more and more complex. There are very few operations that are possible with a nominal variable, but by the time we reach the ratio variable, there are many additional operations that become available to us. So we say that in terms of complexity, the level of complexity is increasing as we go from left to right, or variables are becoming more informative or more sophisticated as we go from left to right. So we just finished a discussion of different types of variables, and we learned that there are 4 mutually exclusive and collectively exhaustive types of variables. These are nominal, ordinal, interval, and ratio, and as they go from left to right in this list, this complexity is increasing. So the question is, why do we need to learn about this? Why is it so important? Why have I spent maybe about an hour talking about these different types of variables? The answer to that question is this distinction between different types of variables is important because not all statistical methods apply to all types of variables. So there is a certain set of techniques that we can use with categorical variables, and those methods, those techniques cannot be applied to numeric variables. And similarly, we have some methods that are specific to numeric variables. They cannot be applied to categorical variables. Sometimes there are overlaps, so there are some methods that can be applied to both types of variables. But we really need to understand which kind of variable we are dealing with before we choose to apply a statistical method. To give you an example, graphs like pie charts and bar charts can only be constructed for categorical variables. For quantitative variables, we need slightly different versions of charts, such as histograms and scatter plots and so on. In some cases, you can construct bar charts for quantitative variables, but the rules of construction are a little bit different. And we typically like to call those charts histograms. We don't call them bar charts. We'll talk about these graphs in more detail in a different session. But the point is that the choice of statistical method depends on the type of variable that you're dealing with. In Education 520, in the second half of this semester, we'll talk about some advanced methods like analysis of variance, linear regression, and t-test. And we'll find out that in order for us to be able to use all of those methods, or variable of interest, which is often known as the dependent variable in a study, must be a numeric variable. You cannot use those methods if your outcome variable or your dependent variable is a categorical variable. Right? So it's extremely important to be aware of this. When you incorrectly use a method that does not allow for a certain type of variable. So for example, if you were to use a categorical variable as an outcome variable in a regression model, the computer program won't give you any warning that you did something wrong. It will still give you some output, And chances are that if you did not realize your mistake, you're going to go ahead, you're going to interpret that output, and you're going to make very incorrect conclusions. You're going to draw very incorrect conclusions. Your inferences are not going to be good. Your generalization is going to be bad. Your estimates are going to be biased. In some cases, they will be completely different from what they are supposed to be. So your numbers will tell a very different story compared to if you had chosen the correct statistical method. So it's extremely important that we are aware of these different types of variables and that we know how to deal with them, that we know the different kinds of operation that can be performed with these variables.